In this lecture, we will discuss the electric field, which is section 2.1.3 in Griffiths. This section we are covering after the Coulombic force, the Coulombic interaction between charges. As a review, we considered a source charge which we represent with small q and a test charge which we represent with capital Q. Now the source charge is not at the origin, but it is at Ri prime distance from the origin, while the test charge is a tilted R from here. Now I have put the index I because here our charge here is Qi here, and that's why I am putting in this one. From this figure, I can see that Ri plus tilted Ri is equal to R. And here, Ri I can write, which is the distance between the two charges. And this is equal to R minus Ri. And as a result, we derived the Coulombic force 1 over 4 pi epsilon naught Q and capital Q over tilted R square in R unit vector direction. Now here, if we consider that the source charge is at origin, then Ri prime will become equal to 0, and we will have the tilted R equal to this R. And we will return to the Coulombic. The general that we usually write is 1 over 4 pi epsilon naught and Q over R square, and this is in R unit vector direction. This is in the situation when we will have the source charge at origin. When the source charge is not at origin, then we will have this situation. Similarly, if we will have more charges here, like for example, we are having other charges, like there is Q1 charge, there is Q2 charge, and Q3, and so on up to Qi charges, then I can write that force is equal, by the superposition principle, I can write that the net force or the total force is equal to all the forces of interaction, which is F1 plus F2 plus F3 and so on. And then this thing is equal, if I take 1 over 4 pi epsilon naught is common from this one, then I will have the Q here, which is here. Q is the test charge is common here, while then the interaction of this test charge with Q1, then with Q2, with Q3, and so on up to Qi, and their respective distances, because this will be Qi and this will be Ri and so on. So this is equal to the first charge, and the first charge will be Q1 and this will be R1 here, and square of this in R1 unit vector direction, and plus Q2 and then in R2 square and tilted R2 plus Q3 divided by R3 square and in R3 unit vector direction, and plus so on up to Qi. So I will have Qi here divided by Ri squared and Ri in the direction of it. So this will be the total force, or this will be the net force that we will have here. We are considering the source charge. Source charge is not at origin. That's why we are using the tilted R. And here this one, if I take this Q here, Q, and then 1 over 4 pi epsilon naught, and all these we add up, then this I define is Q times the electric field. Now whenever we are having a source, then that source will have a field, and that field will exert a force which is equal to the test charge times the electric field, the field of it. In other words, I can write that electric field is equal to force over charge. The force per unit charge. And I will explain you what the unit means. But let's first understand that why we need this electric field. When we are having the Coulombic interaction, when we are having the force between the two charges, then why we need to define electric field? What's the role of electric field? So the answer to that thing is that when we are having a source charge, that source will have a field, and inside the vicinity of that field, or inside that field, that it will cause a force on that unit object. So field is basically a fundamental thing, and after the field, this is a fundamental or a physical thing, and after this one is the interaction between its entity. Whether the entity is mass, then it will be a gravitational field, or it's a charge, it will be an electric field. So that's the whenever we are having a source of something, then that source will have a field, and the field will exert some force. Then we say that electric field is basically the force per unit charge. Here we are having the source is charge. So this is the force per unit charge. Now what does unit mean? Unit, we know that it means 1 here, 1. But we know that charge is having a unit, and this is coulomb. So 1 coulomb, and it depends, means the unit depends on the source charge. Because if, for example, the source charge is in coulomb, then the unit charge will be 1 coulomb. It will not be 1 microcoulomb or 1 nanocoulomb like. When the source is in coulomb, then the test charge will be 1 coulomb. And if the source will be in microcoulomb, then the test charge will be 1 microcoulomb. And when the source will be in nanocoulomb, then the unit charge will be 1 nanocoulomb. So that when we do multiply here, then the test charge is not having its effect here reflected. For example, let me explain this thing more. That for let's say this board is having some charges, some source charge is here, and I'm from here coming to the board, and if I will be having a unit value here, then inside the multiplication I will actually measure the strength of this source charge. Like 10 coulomb is here, and I'm having 1 coulomb, so 10 into 1 will be equal to 10. So I will experience some force from this source charge. If, for example, I'm having 2 Coulomb charge with me as a test charge, means it now not a unit charge, and you go there and you will experience that now the force is double of that. But in reality, the force will not be double of that. Actually, this magnitude is not unity, and we are counting the effect of the test charge as well. So in order to exclude this thing, we will consider the test charge, which we represent by capital Q is unit magnitude, and unit will depend on the source charge. If it will be any of these, then it will be one of this. So this is means whoever will measure the strength of this field, the test charge, if unity will be there, then the magnitude or the strength of this field will be exactly the same. So the test charge is supposed to be unit in magnitude. And now we are in a position to tell that when we have the force, then why we need the electric field. So the electric field is something which is independent of the test charge. The electric field is having its strength, whatever its strength will be. Whether you test it or not, the field is there. So that was the reason to define the electric field in order to get rid of the test charge, because here the force of interaction is mutual. We can't say about the strength of one. So if we consider one of the charge, which we call the test charge, is unity, then we will be able to determine the strength of the source charge. And this one I can further write that F is equal to, this F will be equal to, or the electric field I can write that the electric field from that expression is 1 over 4 pi epsilon naught and summation on charges. I runs from 1 up to any number. Now this I is not that I, but it is just the summation number, and let's say it goes up to n charges, then we will have Qi divided by the Ri squared and Ri unit vector. When I is 1, then we will have Q1 over R1 square and R1 unit vector direction. And this will give us the net electric field or the total electric field here. Similarly, if these charges that we are having here, if these charges are not countable, when they are countable, like I can say 1, 2, 3, 4 and 5, then we will use the summation. They are discrete in nature and we will use the summation symbol. But when charges are not countable, like they are just, for example, like this, now they are not countable. So we are having a continuous charge distribution here, and this continuous charge distribution we will find with the help, means we can sum up these with the help of integration. So for a continuous charge distribution, for a continuous charge distribution, because it will be a distribution, then this capital sigma, this is capital sigma, this will go to integration, and continuity comes in and it will go to integration, and I will write that E of R, and this one is the electric field 8 R here, which is our observation point. This is observation point P here. So E of R is equal to 1 over 4 pi epsilon naught and then this will convert into integration, continuous charge distribution, and then we will have 1 over r square in r unit vector, and this will be dq here, because we will integrate dq is the smallest unit here that we are going to integrate. This is a frictional charge, the smallest possible, and we will integrate this one and we will find the whole charge. And when this thing comes in, then it depends on the geometry, that what kind of geometry we are having. For example, whether we are having line geometry, like on a line charges are distributed, or we are having surface or sheet geometry. Like now the charge distribution is on a sheet, on a two-dimensional surface, on a thin film, or any area containing material. And then we are having, whether it's a surface or it's a volume on which we are having the charge. For example, solid cube, we are having solid sphere, solid cylinder, and the charge distribution is there. So in those situations, we will have this dq equal to, in this case, if lambda is the charge per unit length, then lambda times dl, when this will integrate, it will give us the total charge. So dl will give dq charge, and it will be multiplied with lambda. And if we will be having surface, then if sigma represents the charge per unit area, then sigma times dA will give us the dq. And for a volume, if rho represents the charge per unit volume, then rho d tau. D tau is the frictional volume, and this will give us the value of dq. And we will put it there, and on the basis of this one, we will calculate the electric field. Like for example, in this situation, we are having a line distribution and charges are on a line, and this line is having the charge per unit length, it is equal to lambda. Then we will integrate this one. When it comes to dq, then it will become dl, the frictional length here. And if we are having a sheet, like having some area, then this sheet, some charge distribution is here, and sigma is then the charge per unit area, and we will have dq equal to sigma dA. It is having, we will consider a fractional, we will consider on this area some fractional area, and that fractional area is dA. As we are considering some fractional length here, which will be dl, and we will integrate. And over here, it will be the volume. So let's say, for example, a cube, a solid cube here, and how much is the charge here? If rho is the charge per unit volume, then how much here? If rho is the charge per unit volume, then dq will be equal to rho d tau. While d tau we can write, sometime we write dv, sometime we write d tau for a fractional volume. And this way we will be able to find out the electric field. Let me write the equations for them, but first let's clarify something here. That is, we put the source charge when it is at origin, then it will be like this. But if the source charge will be not at origin, then for DL and for DA and for d tau we will have prime coordinates because they are at r prime distance. I can write for the line geometry. For the line geometry, the electric field at a distance r, mean observation point, is equal to 1 over 4 pi epsilon naught integral, and then this is lambda at where is lambda located? It is at r prime, means it is not at origin but it is at r prime distance, divide by this tilted r square and r unit vector, and here will be dl, and this will be primed. Similarly, for a surface, this will be ER equals 1 over 4 pi epsilon naught in integral, and this will be sigma r prime and r unit vector, then dA prime divide by tilted r square. Similarly, for a volume, it will be r, and this thing is equal to 1 over 4 pi epsilon naught and integral sigma, so it will become rho, and rho at r prime, the volume charge at r prime in r unit vector d tau prime over r squared. So this will give the electric field of a volume charge distribution. So when we calculate continuous charge distribution, then we will have to look what kind of geometry we are calculating on. Whether it is a one-dimensional geometry, which we call line, it's a two-dimensional geometry we call the sheet or area, or when it is a three-dimensional geometry we call volume, or we call its cube or sphere, or they are three-dimensional surfaces, three-dimensional bodies.